So, today we shall consider FSA with epsilon moves. First we consider deterministic FSA, then we consider non-deterministic FSA. Non-deterministic FSA are equivalent to deterministic FSA, and you can simulate a non-deterministic FSA with a deterministic FSA. But the transitions were labeled with symbols from sigma, the alphabet, but today we shall also see that there could be epsilon moves. First let us take an example. Look at this diagram. There are 3 states, Q0, Q1 and Q2. Q2 is the final state and Q0 is the initial state. The transitions are as follows: 0, epsilon, 1, epsilon and 2. The alphabet here consists of 3 symbols: 0, 1 and 2. In Q0, if you get a 0 you go to Q0, and in Q0 if you get a epsilon or without reading any symbol you can go to Q1, and in Q1 if you get a 1 you go to Q1, in Q1 without getting any symbol you can go to Q2, and Q2 if you get a 2 you go to Q2. From the figure, guess what is the language accepted. You can see that a string is accepted if it takes you from the initial state to a final state, whether it is a deterministic automaton, non-deterministic automaton. If there is a sequence of states which take you from a initial state to a final state, that string is accepted. So, you see that you can go along this several times, then you can move to Q1, go along this several times, go to Q2, go along this several times. You need not read a 0 also, straight away from Q0 to Q1 you can go and read only 1s and 2s, or you can just read 0s and 2s alone, or you can just read 0s and 1s and go to Q2. You can just read 0s alone, you can just read 1 alone, you can just read 2s alone. Okay, so the language accepted is L of m or L is 0 power n, 1 power m, 2 power k, where n, m, k are greater than or equal to 0. This is a finite state automaton with epsilon moves, and because we allow epsilon moves, you are able to change the state without reading any symbol. Okay. You can go from one state to another state without reading any symbol. Adding these facilities, does it increase the power of the automaton? Here there are only one arc with 0, you may have another arc with 0 also, that is basically the diagram is non-deterministic in nature. Apart from being non-deterministic in nature, you also allow epsilon moves. Okay, formally defining FSA with epsilon moves, and FSA with epsilon moves is a pi tuple m is equal to k sigma delta q naught f. Same way you define. K is a finite set of states as usual, sigma is a set of input symbols, q naught in k is the initial state, f is the set of final states. The only difference will come in delta mapping. Delta is a mapping now from k into sigma union epsilon, right, into 2 power k subsets of k. Okay. Now, how do we define a string accepted in this case? Basically the idea is it should take you from an initial state to a final state, but formally how do we define? For that we define what is known as the epsilon closure. Epsilon closure of a state, you define epsilon closure of a state. How do you define this? The set of all states reachable from it just by epsilon moves. Okay. The epsilon closure of a state Q is the set of states reachable from Q through epsilon moves including itself. So, in this case what is the epsilon closure of Q naught? Epsilon closure of Q naught is Q naught, that state will be there, then from Q naught you can reach Q1 by epsilon move. So, it will be Q1, then from Q naught through Q1 you can reach Q2 also. So, the epsilon closure of Q naught is Q naught, Q1, Q2. And what is the epsilon closure of Q1? From Q1 you can go to Q1, Q1 will be included, then Q1 by epsilon move you can reach Q2. So, epsilon closure of Q1 is Q1, Q2, epsilon closure of Q2 is just itself. Now, we define extend delta to k into sigma star. Now, you use a symbol delta cap here, right, usually when you extend. And in the case of deterministic automaton and non-deterministic automaton, later on we found that you can use the same symbol delta cap or delta, but here we cannot do that, we will see why. Delta cap Q epsilon is epsilon closure of Q. See, when you usually in the non-deterministic automaton and deterministic automaton, you say delta cap Q epsilon is equal to Q, isn't it? That is, when you are in state Q, if you are not reading any symbol, you will be in the same state if it is a DFSA or a NFSA. But in the case of finite state automaton with epsilon moves, when you are in a state Q, without reading any symbol you can be in Q or you can go to any one of the states in the epsilon closure of Q, isn't it? Just by epsilon moves alone you can go. Suppose you are in Q naught, without reading any symbol you can go to Q1, you can go to Q2. So, delta cap Q epsilon is equal to epsilon closure of Q. Now, if you have a string WA, a string W and a symbol A, how do you define delta cap Q WA? This you define as epsilon closure of some P. P is a set of states P, where what is P? P is a set of states P, small p, for some R in delta cap QW delta of RA contains P. You define delta cap Q epsilon is epsilon closure of Q, then WA, take a string WA. How do you define delta cap Q WA? What this essentially means is, starting from Q, after reading WA, what are the possible states in which you can be? That is what it means. How do you define that? It is the epsilon closure of P, where P, this is capital P, to make a difference, this is the set of states P, set of states P. What are the states P? For some R in delta cap Q W, delta of RA contains P. What this essentially means is, supposing there is a string W A, starting from Q, after reading W you can be in a set of states, that is denoted by delta cap QW. So, R is one of them. From R, after reading A, you can go to some sets of states P, some set, certain sets. Now, from such sets you can also make some more epsilon moves. Okay. So, you consider the epsilon closure of these states, you can just read epsilon and go to some more states also. All these states will be in the epsilon closure, P itself will be in the epsilon closure of P. Okay. So, starting from Q, after reading W you can be in a set of states. Okay. In between you may be making beginning or in the end you may be making epsilon moves. R is one of them, say. So, you consider all the union of all such moves. From R, after reading A you can go to state P, but afterwards also you can make some more epsilon moves, right. So, what it means is, for some R in delta cap QW, delta RA contains P, then afterwards it can make some epsilon moves, that is why you write it as epsilon closure of P. Okay. So, the language accepted. So, this it is easy to remember, I will rub up. So, the language accepted is T of M or L of M, sometimes it is also denoted as L of M. This is the set of strings W, W belongs to sigma star, delta cap Q naught W contains a state from F. This is the way the language accepted. Okay. Now, you see that, for example, delta of Q naught 0 in this example is Q naught, okay. But what is delta cap Q naught 0? Starting from Q naught, what are the possible states you can reach after reading a 0? You can reach Q naught, you can reach Q1, you can reach Q2. So, this will be Q naught, Q1, Q2. They are not the same. See, in the case of NFSA and DFSA, when you restrict it to symbol, they become equal. That is why you can use the same symbol. But here they are different. So, you cannot use the same symbol. Delta cap has to be differentiated, I mean it is different from delta. You have to use two different symbols here. They cannot be the same. Now, let me take delta, what is delta cap q naught 0 1. What does that mean? Starting from q naught, after reading 0 and 1, what can be the states in which you can be. So, starting from here, after reading 0 you can go here, after reading 1 you can go here or q there, is not it. So, the answer is q1 q2. Using the formal notation, how do you get this? This is equal to epsilon closure of the set of states delta of delta cap 0 comma 1. Sorry. Delta of delta cap q naught 0 comma 1. In this way, if you write using this formal notation. So, what will be this be? This is epsilon closure of, what is delta cap q naught 0? Q naught q1 q2, all from q naught after reading 0 you can be q naught q1 q2. So, this will be delta of q naught q1 q2 Now, for a single state we have defined this. When you extend it to multiple states, what can you say? Delta of R A, where R is a set, that you by definition you can define. This is defined. Delta of R A is union of Q belonging to R delta of Q A, right. If you have a set, from each one what are, so you have a, initially you can be in a certain set of states. After reading A, what can you be the, what can be the set of states in which you can be in? Starting from this, what are the states? Starting from this, what are the states? Starting from this, what are the states? So, find the union. And similarly for strings, delta cap R W, R is a set of states. From these set of states, if you read W, what are the possible states in which the machine can be? This will be defined as union of Q belonging to R delta cap Q W. So, you have extended delta to delta k into sigma star and you called it as delta cap. When you want to extend delta and delta cap to a set of states, you extend like this. Okay, using this definition, what is the epsilon closure of delta of, I did not write that 1 here, forgot to write the 1 here, okay. This one. Delta cap q naught w is q naught q1 q2 and this one is here. So, what is delta of q naught q1 q2 1? It will be delta of q naught 1 union delta of q1 1 union delta of q2 1. But you find that delta of q naught 1 is empty, delta of q1 1 is q1, delta of q2 1 is also empty. So, from these 3 states, only one of them will lead you to a final one. So, that will be epsilon closure of, here it will be phi union q1 union phi, it will be like this. So, that will be epsilon closure of Q1 really, and what is the epsilon closure of Q1? That is equal to Q1 Q2. So, starting from Q0 after reading a 0 and 1, what are the states in which you can be? Look at the diagram, it is very clear, you can be in Q1 or Q2, but formally using the definition, how do we arrive at that? We arrive at it like this, right. Now, it looks as though by adding the epsilon transition, the power, I mean you are giving more power, right, epsilon transitions, but the power is not really increased, the same language you will get, you will not get anything more than the non-deterministic FSA or deterministic FSA. So, the idea is given a NFSA with epsilon transitions, you remove the epsilon transitions, right, and get an NFSA without epsilon transitions. So, how do you go about it? Let M is equal to K sigma delta Q naught F be NFSA with epsilon moves. Then NFSA without epsilon moves, M dash can be constructed such that the language accepted is the same, T of M is equal to T of M dash. That is, you are trying to remove the epsilon transitions without changing the language. Now, how is M dash defined? M dash has the same set of states K, same input symbols, okay. Then mapping you have to define delta dash, the same initial state you have Q naught, final states will be changed F dash, okay. So, if you do that, how do you define F dash, how do you define delta dash? F dash is F if epsilon closure of Q naught does not contain a state from F. If the epsilon closure of Q naught does not contain a state from F, it is the same as F. It is equal to F union Q naught if epsilon closure of Q naught contains a state from F. When will a string epsilon be accepted by the machine? A non-deterministic FSA without epsilon transition, if the initial state is a final state. But NFSA with epsilon transition, epsilon can be accepted if the epsilon closure of Q naught contains a state from F. So, in this example, see epsilon will be accepted. Starting from here, you can reach a final state without reading any symbol. So, epsilon is accepted by the machine. Now, if you want to construct an equivalent machine and if it has to accept epsilon, then you have to make the initial state a final state, right. So, just for epsilon alone the difference is made, otherwise it is the same set of final states you have. If you want to accept epsilon, the empty string, then make q naught as the initial state, otherwise q naught as a final state, otherwise leave it. How do you define delta dash? Delta dash QA, A is a symbol, Q is a state, is defined as delta cap QA. Okay. That is, starting from Q, what are the states in which you can be in A after reading A, that will be the here. Okay. So, in this example let us define. So, let us look at this example. What the set of states are the same. This is M. How do you construct M dash? Q naught, Q1, Q2. Now, this is the initial state, and because epsilon is accepted, this will be a final state and this also will be a final state. Set of states are this, because epsilon is accepted, this is made a initial state and this is already a this is a final state, this is also the initial state. This state is already a final state, right. Now, from each one you have to find the arcs corresponding to 0 and 1 and 2. What is delta of q naught, delta dash q naught 0? From q naught after reading 0, what are the states in which you can be in? Q naught, q1, q2. So, there will be one arc q naught like this, there will be one arc like this, there will be one arc like this. Starting from q naught, after reading a 1, what are the states in which you can be? After reading 1, q1 or q2. So, from here there should be an arc here, I will mark it like this. That means, from q naught if you read a 1 you go to q1. From q naught if you read a 1 you should also go to q2, right. That is, starting from q naught after reading a 1 you can be in q1 or you can be in q2. So, from here 1, from here again 1. Starting from q naught after reading a 2, where can you go? After reading a 2, 2, right. So, from q naught there is an arc with label 2 going to q2. From q1 after reading 0, where can you go? There is no map, it is empty. So, you need not have to draw an arc. From q1 after reading a 1, where can you go? Either q1 or q2. So, there will be an arc with label q1 here, there will be an arc with label q1 here. From q1 if you read a 2, where can you go? From q1 you can go to q2 and read a 2, is not it? So, from q1 if you read a 2 you can go to q2. So, there is also an arc from q1 to q2 with label 2. Okay. From q2 you cannot read a 0, you cannot read a 1, but if you read a 2 from Q2 you can go to. So, this is the NFSA without epsilon transitions, which is equivalent to this. The language accepted is the same. Just see 0 power n, 1 power n, 2 power n can be accepted, because first one you can first 0, I mean the first, any number of zeros you can read, 1 0 you can read, any number of 1s you can read, 1 1 you can read, and any number of 2s you can read, right. If you do not want to read 1s, only 0s and 2s, starting from here read any number of zeros and then 2s, you can omit 1 also. So, anything it is 0 power n, 1 power m, 2 power k, where n, m, k are greater than or equal to 0. Now, let us go to the formal proof. We show that delta dash q naught w is equal to delta cap q naught. In the machine m dash, after reading w starting from q naught, the set of states is the same as starting from q naught in m and reading a string w. This will not hold for epsilon. Okay. This may not be true for epsilon. This you have to prove using induction, but for epsilon alone this may not hold. So, induction should start from length 1. You have to prove this by induction on length of w starting from 1. It will not hold for 0, is not it? Here delta dash q naught epsilon is q naught only, is not it? Delta dash q naught epsilon is q naught only, whereas here delta cap q naught epsilon is q naught, q1, q2. Okay. So, epsilon, that is why if epsilon is accepted you have to make the initial state also a final state. Start from induction on length 1, you say delta dash q naught a is the same as delta of q naught a. This is by definition. How did we define? For any q we defined like this, is not it? The definition was like this. So, basis class, this is the basis class. By definition it has been defined like this, so it is okay. Okay. Now, assume w is equal to some x a, and by induction hypothesis delta dash q naught x is equal to delta cap q naught x. The result holds up to string of length n, this is string of length n plus 1 and so on. Okay. So, assume that the result holds up to string of length n, w is a string of length n plus 1, x is length n, say a is 1. So, now this is a set of states, say some p. Now, what is delta dash P A? This is union of P in P delta dash delta dash Q naught W A is equal to delta dash P A equal to union of delta dash P A. So, epsilon closure of union of P in P delta cap P A equal to delta cap Q naught X A. Now, you have to show that if delta of Q naught X contains a state in F, if and only if delta cap Q naught X contains a state in F, delta dash F dash. Now, starting from Q naught, after reading X, you are in a state QF, say here. The same thing will happen starting from Q naught, after reading X, you will be in a state, the same state QF. This is for any other string, but if it is epsilon, if X is epsilon, purposefully you are making the initial state a final state if epsilon has to be accepted. So, epsilon, if the original machine accepts it, it will be accepted by this machine. But if X is different from epsilon, starting from Q naught, because of this result, you will see that starting from Q naught, if you are able to reach a final state, here also starting from Q naught you will be able to reach a final state. And starting from here, if you are able to reach a final state here, starting from here you will be able to reach the same final state here. But there should be one difference. The one difference is in this, if you accept a string X starting from Q naught by going to Q naught, and Q naught has been made a final state because epsilon is accepted. Q naught is a final state here. Q naught is not a final state here, but Q naught is a final state here. And a string X is accepted here by going from Q naught to Q naught. Here also by going here X, you will be able to go from Q naught to Q naught, but here Q naught is not a final state, right. This particular case you have to distinguish, and in that case what happens is, how did you make Q naught a final state? Because the epsilon closure of Q naught contains a final state. So, there will be another state QF, and the epsilon closure of Q naught will contain that QF, right. And that QF will also be a final state here. So, starting from Q naught after reading X, you may go to Q naught, but you may be able to, you will be able to go to QF also here. Okay, that is the only difference. If you are able to go from Q naught after reading X to Q naught, it will be possible for you to go to QF also starting from Q naught. So, if a string is accepted by M, it will be accepted by M dash, and if the string is accepted by M dash, it will be accepted by M. So, the language accepted is not affected. So, we have this result T of M is equal to T of M dash. So, so you have the same construction we have followed here. So, in essence we have proved 2 steps in the diagram which we have considered earlier. This is, you have DFSA and you have NFSA and you have NFSA with epsilon moves, and you have regular expressions. We have not formally defined this, but we have already seen what is a regular expression in examples. For example, in this one the language accepted is 0 power n, 1 power m, 2 power k, n m k greater than or equal to 0, and this the regular expression will be 0 star, 1 star, 2 star, right. There is a string of zeros followed by a string of ones followed by a string of. Now, what we have earlier seen is, given an NFSA, how to construct an DFSA. This is by what is known as a subset construction, and given a NFSA with epsilon moves, how to construct a NFSA without epsilon. That is what we have seen today, how to remove the epsilon transitions. So, given a NFSA with epsilon moves, you can construct a NFSA without epsilon moves, and from that you can construct a EFSA. But if you are given a problem to construct a DFSA, it is better to start straight away constructing the DFSA, because if you can do this, you can do this and then convert this, and it will take lot of time, and the number of states also may be very much, because from here to go to here, from n you may go up to 2 power n. And these two we have to prove, given a expression, how regular expression, how to construct the NFSA with epsilon moves, and given a DFSA, how to construct the regular expression. These two portions we have to see it. The language accepted by all these three is the same, it is the regular, it is called a regular set. The language represented by this, see, you say that the language accepted by these is this, the language represented by a regular expression is this, a regular set, and a language generated by type 3 grammar or a right linear grammar or a left linear grammar. Generally you do not consider this so much, is a regular set. So, there are 3 ways of defining a regular set, either by means of acceptance by a finite state automaton, either DFSA or NFSA with epsilon moves, or it can be represented by what is known as a regular expression, or it can be generated by a type 3 grammar or a right linear grammar or a left linear grammar. What is a right linear grammar? If the rules are of this form, this is called a right linear or a regular grammar. Of course, when you want to accept epsilon, you must make a slight distinction. S goes to epsilon, you must allow, or sometimes A goes to epsilon also you may allow, it does not matter much. In the case of regular sets and context free grammars, it does not make much of a difference if you include epsilon on the right hand side. but only type 1 grammar epsilon should not be on the right hand side, and if you want to include epsilon you must be very careful. Okay. So, next we will consider regular expression.